Hi all, in this one I'm going to give you an intuitive explanation for the existence of the gradient, and we'll also focus on understanding what it represents. So intuitive, not too much math. So let's begin by building up a coordinate system. This might be my z-axis. We still need the basic 2D depiction of a 3D coordinate system. That's my z. For example, we'll say this is my x and this is my y over here. Next, we need to have a surface so that we can climb along the surface somehow. So for that reason, I'm going to draw in something that kind of looks like this, but I just need to make this thinner so it fits better. Yeah, so this is a slice of a surface, okay? So we're taking a surface and we're slicing across the surface, or if you like, a solid in 3 dimensions. And then let's also do this on the bottom. Again, it's like taking a slice, so it looks like this, and then connect the sides up. Let me erase that little piece there. I don't need that 100%, this right here. So we're going to climb along the surface. Now, to make things more clear, I'm going to call this the top, the red line. And it's also at the bottom, so that's going to be this one right here. What I'm going to do is I'm going to climb. How am I going to climb exactly? I'm going to climb from the bottom, which is kind of traced in black here, to the red on top. And again, I can do this in a variety of ways. Let's think about this for 1 second. Imagine I begin on this point. It's an arbitrary location to begin. I have a rope and I want to climb the cliff, so to speak. So I can do this, for example. I can do it along this line here. So I imagine a little person walking this way. I can probably do that. It's not too hard. It's climbing. Okay. Or the other option, for example, would be take a longer journey, like for example this one here. For both of these, as you can see, you're going to get from the bottom, this traced over right here, to the top, which is the red. You're going to get from the bottom to the top. Here the experience would be perhaps a little bit different because it's gentler. Okay, you're doing it perhaps over a longer distance. And one last thing that we could try to do is be very adventurous, so to speak, and just climb. So basically like this way, straight up almost. Now that would be tricky to do, right? That would be almost, dangerous because it's almost straight up. What does all of this tell us? Well, it tells us that now we can complete little slope triangles. What I mean is, I can imagine something like this. For this first leg, this one right here that is, the one that I drew first, imagine I'm climbing this way. I can draw and complete a little slope triangle that says if I did this and then I went up. And I'm doing that because then you can measure the slope. Remember back to basic algebra, perhaps you saw little slope triangles. This is exactly the same concept, but it's for 3 dimensions, that's all. So that's for this one. I'm going to call this horizontal leg right here. Let me trace over in yellow. I'm going to call that, well, we can give it whatever name we want. So I'm going to call this, for example, A. This right here, this is the vertical change. I'm going to call that the delta Z. The specific value itself is not too important. Okay. Notice that because we're going from the bottom to the top, this delta Z portion will be the same for all of these triangles. So what I mean, for this one, the horizontal leg would kind of appear to be coming out a little bit. And then you would go this way. So what is the same here is the following. This right here. This is the same delta Z. There's only one vertical change. So let me zoom in. This is delta Z over here. The same delta Z as for the other one. And the horizontal leg, let me zoom in here. That's this right here. Both of these horizontal legs are parallel to the XY plane down below. Keep that in mind, okay? Let's also do this for the last leg of the journey. So again, for this one, it's going to be the same delta Z because you're going from the same point to the same distance above that point. So it's the same change. So I'm going to first draw that in here. Let's see, it's going to be roughly this right here. Okay, so that's about this. In the horizontal leg in this context, that's going to look like about this right here. And now this represents the same delta Z as for the other ones. The same change in the height, the change in the value of Z. And the horizontal leg here is this. Let's give some names to these things so we can track them. So the first one was A. I'm going to call this one A double prime. I'm going to call this one A triple prime. Let's call this one A prime. We have essentially, if you think about this, 3 different triangles. Once you have triangles, then you can compare the slopes of the triangles. That's all. You can tell intuitively, clearly, that's just by looking at the picture that from here to here would be the hardest. But at the same time, it would take you the fastest from the bottom to the top. Because this leg is longer, so it would obviously take more time. This would take perhaps more time also, right? It's longer. Let's take these and draw them on the side. So I'm taking the triangles and I'm going to draw them on the side here so you can study and compare them. And also for the sake of simplicity, arbitrarily what I'm going to do is I'm going to define delta z to be 1. Make this 1 and the same delta z is 1. So just for the sake of simplicity, I'm defining the change in the vertical to always be 1. And let's also assign some values to the yellow legs of each triangle. Arbitrarily, what I'm going to do is, let's see, since this is delta z equals 1, we don't have to be too perfect. Imagine this is also 1, so maybe this one here is like 0.5, it's a half, maybe less than that. Specific numbers themselves are not too important. And the a triple prime, well, that's longer than a prime or a double prime, clearly. So for the sake of simplicity, I'll make it 3. Okay? So let's take these triangles from our 3-dimensional space and put them in our 2-dimensional space and arrange them. So for example, I'm going to begin with a prime that has a leg that goes about this way, and then one that goes about this way. So here, again, this is like the horizontal leg, and this represents the vertical leg. This is your delta z equals 1, and the bottom there, that's a prime equals 1, which tells you that the slope that this represents, just calculate the slope the way you've learned how to calculate slope in basic algebra. So you simply form delta z, the change in the vertical over the change in the horizontal, a prime. So that's 1 over 1, which is just 1. That's the slope. Do the next triangle. So that next triangle, the one with the a double prime over here in the base, right here, I'm taking that triangle out of the shape and placing it next to the other one. So that's going to give us a triangle that looks like, it's pretty short this way, but it's got the same delta z this way. Okay, so let's emphasize this. This is still delta z equals 1, but the horizontal leg here is only equal to, let's see, this is a double prime equals 0.5. So when you form the slopes, again, delta z over a double prime. So that's going to be 1 over 0.5, which is 2. So that slope is twice the previous slope. Let's repeat this for the last triangle. So again, that's the last triangle is this one, right here. I'm taking that out of the 3D shape and I'm going to just draw it over here in 2 dimensions so we can look at the slope. So that's going to look like, that's got a pretty long horizontal leg, and then the same delta z as for the other two. So that looks like that essentially. And let's trace over the relevant bits. So this is the leg for that one, and then this is the delta z. So the delta z again is 1, and the horizontal leg for this one, well, let's see, that's a triple, that's 3. And when I compute the slope for this triangle, it's going to be delta z as before over a triple prime. So again, it's just a slope, nothing else. 1 over 3, which is about 0.33, more or less. So you see that of all of these, there's one winner that clearly emerges. The winner is this one right here. Okay, that is the one that has the biggest slope. And it's not surprising, perhaps, just by looking at the picture intuitively, you can tell that it corresponds to this triangle, because you're going straight up from here to here, which in terms of a triangle means a leg this way and then a leg this way to get to that point. So that slope is the steepest. It gets you from the bottom to the top the fastest, compared to, for example, going along this longer leg, or going, for example, along this longer leg here. One more thing that we should talk about is to relate this to the gradient. The gradient says that the fastest way to climb is to find the gradient and then the magnitude of the gradient. The magnitude of the gradient essentially comes from, in terms of these pictures, using the middle picture. This one right here, okay? Because that's the one with the biggest slope. Another aspect that's relevant is the direction. So what I mean by that is, I'm going to take this picture here, I'm going to draw some level curves. So level curves are just projections down to the XY plane. Let's do the top level curve. And here I have to be really careful, things can get really distorted. So let me project this down. So it's going to project to about here. Project that down to about here. So that's going to be the projection of the red curve. Let me draw that. It looks like this. In the XY plane. So it's as if a line were above the surface shining straight down and casting shadows to the XY plane. That's the way to think about a level curve. And then this green one that I'm again tracing over just to emphasize it. When I project that to the XY plane, it will look like this one here. And a question naturally enough might be, what's the fastest way to go from the green level curve to the red level curve? So you do that simply by asking yourself a question, okay? Let me trace back over these. That was this leg for this one. That was this leg for this one. So let's draw the depictions, the projections down below. That will look like this. The projection of a double prime down below is this right here. This is basically A double prime, see? Let me erase that bit of a straight line. The projection of A triple prime, so let me emphasize this point. I'm projecting A triple prime right here. That would be from here to about here. That's that projection. And the projection of A single prime, well, let's see, that would be about here. This is A single prime, A prime. And you can tell just by looking at this that if you were a little person and you had to go from here to any of these other points, like point A, B, or C, if you were to go to A, B, or C, the fastest possible way to do that, to go from the green to the red, would be to go across this way right here, because that distance is the shortest, so it would take you obviously the least time. Now you go from here to here. I want to be careful about not including time in here. So this is all just in terms of space, X, Y, and Z. This also tells you that there's a direction involved. And the direction maximum increase, as you might have learned, is basically the one given by the gradient. And we see that over here because you see that since this line here corresponds to this line here, which corresponds to this triangle, and then the fastest rate of climbing, that the direction of this line is the line that tells you how you should go so that you get to the next level on your, for example, surface the quickest possible way. It's this one right here. And not this other one clearly, right? Which corresponds to this triangle, which corresponds to this climb. See that? Which is clearly slower. Just like this one over here corresponds to this bottom, which corresponds to this climb, which is clearly slower because this would, it's gentler over here, okay? So the direction of maximum increase is the one given by the gradient. And the value of the gradient is the maximum slope, and that simply corresponds, roughly speaking, to forming the ratio of this over this. And because this here is as small as possible in that case, essentially, that means that the ratio of this to this is as big as possible, so we're climbing as fast as possible. And that's not the case for the other ones. Okay, let me zoom out so you can see everything from top to bottom. Thank you so much for watching. I hope this has given you some insights. Please leave a like,